Continuing on for number 4, we have the same idea happening here. We have, in this triangle, we want to find x and 3.6, so you do x divided by 3.6 or 3.6 divided by x. It's kind of nice to have the variable in the rear, though. We're all in terms of centimeters, so we know that we don't have to do any unit conversions, so therefore we don't have to write the centimeters. Equals, we want to match it up with the other triangle. Now it looks, since this is the quote-unquote horizontal segment, that would indicate intuitively that it matches up with 10, since it's the other quote-unquote horizontal segment within the triangle. That's not necessarily true. In fact, it ends up being that it is, but that may not always be the case. So let's use our similar statement again to help ourselves out. X is the segment RS. So in this in this similar statement, RS is the second and third letter, so therefore it matches up with RV. So RV is that segment, which is 10, so 10 matches up with the X. And then our second segment that is in the denominator of the first ratio is ST. S is our third and T is our first, so we want to do our first and third letters, which is QV, which matches up with that, which would be 6. And we cross multiply and solve. 6x, 6x equals 3.6 times 10 is 36, divided by 6, x equals 6, and I remember the units this time, centimeters. For the next part, we have a little more challenging way of, or a little more challenging problem. It's not as straightforward as it may look. They want to know what is the scale factor. Now what's important is to say every dimension of the rectangle is multiplied by a scalar factor. So when they say every dimension, note for a rectangle we have the length and we have the width. So let's look at a specific example. I have 90 inches squared. So an easy number, or two easy numbers, that would give an area of 90 inches squared would be 10 inches and 9 inches. So if I do 10 times 9 inches times inches would give us inches squared, would be 90 inches squared. But we want to know what figure would give a 10-inch square, or 10 inches squared area. Well, we could do many different ones, but what my point be, I apologize, I'm going to back up a step. I don't want to do exactly that with the second triangle because the numbers aren't going to be as intuitive. So my point is that we have inches squared here, but what they're talking about, every dimension, meaning the length and width, is what we're looking for in terms of the scale factor. So it's not as straightforward from doing the ratio of inches squared. We want the ratio in inches because that is the unit of the dimensions. So if you have inches squared, which we have here, in order to get inches, we have to square root it because the square root of a square cancels. So if we have 90 over 10 inches squared over inches squared, and we square root it, that will now give us the correct ratio for inches. The reason is that, again, we don't want the ratio of inches squared, we want the ratio of inches. So to get the correct units, we have to square root it. Now, 90 over 10 reduces, and that will give us 9 inches squared, and the square root cancel to be 3 inches, which is a scale factor of 3 to 1 for the inches. Now, we have to be careful here. We want to figure out what the scalar factor is, what we multiply to go from a larger area to a smaller. So do we multiply by a third, or 3 over 1, or 3, or 1 to 3 to make something smaller? We want to multiply it by a third. So I'm sorry I'm taking up a lot of room here. We don't want 90 over 10. We really want 10 over 90, given this information. Square root. Those cancel, and we have the square root of 1/9 and that gives us the scalar factor of 1/3. That is the scalar factor that we're looking for. So two things going on. We have to convert the units correctly to get the correct scalar factor by square rooting, and you have to make sure you have the correct ratio, whether it's 9/1 or 1/9. How did I know to make it 1/9? Well, we wanted to make the area smaller. So do you multiply it by 3 or 1/3? You multiply it by 1/3. So let's go ahead and look at number 2. The triangle has an area of 20 inches squared. Every dimension of the triangle is multiplied by a factor, and the new triangle has an area of 180. So it's getting larger. So do we want the scale factor? Do we want 180 over 20, or do we want 20 over 180? If we want it larger, we want a number that's greater than 1. So we do 180 over 20. Note it's in inches squared, and we're talking about every dimension, meaning the base of the height of the triangle. The half, base times height, that's the formula for area. The half is not relevant. We only have to concern ourselves with the units of the base and the height. So to get from inches squared to inches, we square root. These cancel, and the 180 over 20, those reduce, and we have the square root. 18 over 2 reduces to 9, and the square root of 9 gives us a scalar factor of 3/1. Applying this down to the number 1, what are the new dimensions of the rectangle B? Well, they say that we have a scalar factor of 2. Meaning we're simply taking, now this one's a little nicer because we have the lengths of the length and width, or the base and height of the rectangle, rather than having to go from the area. So this is nice and neat. If we have 2 centimeters for A and we're doubling it, that gives us 4 centimeters for B. If we have 6 centimeters for B on the top segment, then we have 12 centimeters for B up here. For number 2, what is the ratio of the corresponding sides? It is 2:1, as we see. If we're talking about from B to A, or one way, that's one way you could write it, or 1:2 from A to B. If we did proportions, that would match up the same. So if we had 2/6 over, let's say, you know what, scratch that, never mind. We're not going to look at that. Okay, I think we get the idea. Hopefully we do. Okay, so let's go ahead and complete the table for rectangle A and rectangle B. Rectangle A, the perimeter, we simply add up all the sides. This is 6 and this is 2, so I have 8, 16 for the perimeter. For rectangle B, the perimeter would be 12 plus 4 would be 16, and then we have that again, which would be 32. And we see the perimeter is in a ratio of 1:2, as we talked about. If we're going from A to B would be, the perimeter is a ratio of 1:2 from A to B. How is the ratio of perimeters related to the ratios in problem 2? Meaning, how is the perimeter ratio related to the ratio of the sides? They are the same. So side ratio is equal to perimeter ratio. Okay, number 6, it says what is the ratio of the areas? So first, let's figure out what the areas are. For triangle A, it is 2 times, or excuse me, rectangle A is 2 times 6, which gives us 12. And then here, for B, it's 4 times 12, which is 48. And what is the ratio of the areas? If we do A to B, that would be 12 over 48, which reduces to 1/4. And how is the ratio of the areas related to the ratio in problem 2? Again, problem 2, the ratio is 1:2. Now, how do you get 1/4 from 1/2? Well, you square it, which would give us 1/4. So the ratio of the the ratio of the sides, squared. If I take the ratio of the sides squared, that's going to give you the ratio of the area. And we already, I apologize, the notes are structured this way. This is kind of going backwards because I had to kind of talk through that. on the word problems before, but in terms of the ratio of the areas is always equal to the ratio of the sides squared. And note, before we had the ratio of the area, so to get the ratio of the sides, we had to square root it.